6 in Module 1, Algebraic Expressions, the Distributive Property, is going to focus on two instructional outcomes. The first one, the use of structure of an expression, including the distributive property, to rewrite it and prove equivalency of expressions. And then the second one is to use a geometrical model to illustrate the product of two given factors. So when we look at this idea of the distributive property, by definition it says if A, B, and C are real numbers, then if I multiply A times the B plus the C, then I'm going to get A times B and then A times C. The way students have typically illustrated this in class is we'll draw a little arrow here to illustrate the A times the B, and then another arrow right here to illustrate the A times the C. But the question in this particular lesson is, how would you represent this particular property with a picture? And so I can take this idea or this notion from geometry that I could draw a rectangle or a box, and this idea of length times width, where I would write my A here and then my B plus my C, again defining this as length and describing this side here as my width. And so a lot of times what your teacher will tell you to do is everywhere you see a plus sign or a minus sign, to go ahead and take that box and cut it in half. And so if we wanted to replicate what we saw in the distributive property, the arrow here, A times B, well, A times B is AB, and then A times C is AC. After the teacher models this, they'll encourage the students to try a few on their own. What if we gave you M times N plus P? What would that given picture look like as a model? So again, we're encouraging the students to go back and look at what the teacher modeled in class, and note that we have M by itself on the outside, N plus P, very similar to what was there. And so we could write M and then N plus the P, draw our line, multiply, so we get MN, and then M, and then P. So if we wrote our final answer, it would be MN plus MP. The teacher then will encourage the students to look at this problem here. This time you notice the difference is it brings numerical values or numbers into the piece. So our student may feel very comfortable with just taking and saying, oh, well, that is just 2x, and this value right here is 2 times 3, and that is 6. Now remember, we're encouraging the students to see, can they represent this with a geometric model? And if that's the case, then all they're going to do is draw this box. Put the 2 on the outside here, the x plus the 3, draw our line. 2 times x is 2x, and 2 times 3 is 6, and thus we have the same answer utilizing a geometric model. It's important for the student to look at both the distributive property and this geometric model, because when they are assessed, they will be expected to demonstrate both styles, both geometric and algebraic models. And so in exercise 5, a student named Leela is convinced that if she has a plus b squared, then that's going to equal a squared plus b squared. And so the teacher may start the conversation off by asking the students, what do you think? Do you believe she's right? Do you believe she's wrong? And then ultimately we want them to illustrate a picture to demonstrate their reasoning. Now, as it turns out, before we get started, Leela is going to be wrong. So this is not correct. This misconception is something a lot of students have, that if you have this exponent, I can just take and multiply this 2 here and this 2 here to get this and this. But that's not quite correct in what we want. And so we want the students to illustrate a picture to model what's happening here. And so if we do have a plus b squared, the conversation comes on as what does it mean to be squared? And so a lot of times the teacher may give this offhanded example. If I had 3 squared, then what does that mean? And most, if not all, students say, oh, well, that means 3 times 3. And then the teacher may go one more time and say, well, what if we had 4 squared? And students would say, well, that is 4 times 4. And so going back to a plus b squared, teacher's going to say, well, if 3 squared is 3 times 3, and if 4 squared is 4 times 4, then what is a plus b squared? And the goal is to get the students to realize that it is a plus b times a plus b. Now, given that this first factor has an a plus a b, and this second factor has an a plus a b, when we go and we draw our box, we're going to actually draw a square to give ourselves more space, and we'll write an a plus a b on the side, and an a plus a b at the top. And then we'll section off each part like so. And so when the students go in and they multiply, they see a times a, and they'll write a squared. A times b is ab, b times a is another ab, and then b times b is b squared. Then the teacher is going to say, well, to write the final answer, what we're going to take and do is pull this a squared out. So we have a squared. We're going to look at these two boxes, the AB and the AB, added together is going to be 2AB, combining like terms, and we'll keep this third or final box together, plus B squared. And as we can see, that is not at all like the misconception that Leela had when she considered the answer of being a squared plus b squared. And so this geometric model allows the students to kind of see that difference and understand why it is not the same. The teacher will then encourage students to try some more, such as m plus n squared. Now, m plus n squared, without working that one out completely, is going to be the same as this one. All we did to allow the students to think it through is change the a out for m and the b out for n, so they can get a very similar model or an example to think about what the answer might be. So they would have written down the synonymous ID of m squared plus 2mn plus n squared for this model here. Then the teacher is going to challenge with numbers. And this is where the students really start to kind of think about what's going on and how might it play out. So if we look at the case with numbers, we've got the x plus 2 and the x plus 3. We want to be able to see the student say, well, the first thing I need to do is draw a box. I realize that the first factor has a term here and a term here. So I would expect an x plus a 2, and then I have a term here and a term here, so then I have an x plus a 3. This allows the student to observe that I'm going to need to divide this up into 4 parts, and then when I multiply, I get my x squared. X times 3 is 3x, 2 times x is 2x, and 2 times 3 is 6. When they write the final answer, they'll keep this box to get x squared. Combine like terms, 3x plus 2x is going to be 5x, and then keep my 6 at the bottom to get my final answer. The last set of examples is exercise 6, where it says to draw a picture to represent the expression a plus b plus 1 multiplied by b plus 1. And so it expands on the idea that this factor here has 3 pieces in it versus this factor having 2 terms. And so it does modify our box a little bit to where rather than it being a square, we're going to draw a rectangle. Now I could put this on the side or the top. I'm going to choose to put it at the top this time, where I write a plus b plus 1, and I'll write the second factor, b plus 1, here at the side. And again, each time that I observe a plus sign, I will draw a corresponding vertical or horizontal bar to divide it up. And this time you see that I have 6 individual boxes to compensate for what is happening. And then when I fill it in, b times a, or a times b, is ab. B times b is b squared. B times 1 is b. 1 times a is a. B times 1 is b. And then 1 times 1 is 1. So now the students have to be careful. They have to look and see what are like terms and what are not. So we have AB. There are no other boxes with AB, so we'll just write that down. We have an A and we have a B squared. Well, those aren't like terms, so we write plus A and we write plus B squared. Now it does turn out that these two here are like terms. And so we'll put into our answer not B, but 2B. And then we'll keep the 1 for plus 1. After modeling that, the teacher is going to allow students to try a few by themselves. For example, this one right here, where we'll take a look at an m plus an n plus a 2 multiplied by an n plus a 1. And so we'll draw the same rectangle that we had before. And we'll put m plus n plus 2 at the top, and then an n plus a 1, divide it up, and we'll multiply. M times n is mn, n times n is n squared, and n times 2 is 2n. Second row is m, n, and then 2. So when I write down my final answer, you have mn plus m plus n squared. Now be careful right here. This is a 1n and a 2n. When we add that together, we're going to get 3n and then plus 2. The last one is another one, again, very similar in design, to where we will take and draw another particular box. We'll write the x plus the y plus the 5, and then the x plus the 5. So when we fill it out, x times x is x squared, x times y is xy, x times 5 is 5x, 5 times x is another 5x, 5 times y is 5y, and 5 times 5 is 25. So when I write down the answer, you get x squared. We have like terms in a different order of notation, so we might want to note that this is a 5x and this is a 5x. So when we write down our answer, we'll just keep this xy right here. But 5x plus 5x is 10x. 5y does not have a like term, and neither does the 25. With this lesson, if you want additional practice, I would encourage you to go back and look at some of the squares that I pulled up or down, you can always pause this video, try some for yourself, and then press play, and then check your answer versus mine to see if it is correct. As additional practice for closing, the students were offered the opportunity to consider this expression, the x plus y plus 3 times the y plus 1, where in part A they would draw a picture, and in part B to attempt to write an equivalent expression by applying the distributive property.